Okay. Good morning, all. Am I audible? Can you hear me? Am I audible?
Yes, sir.
Okay. Thank you, Harsh. Okay. So just I'm summarizing whatever I have discussed in the last class. Then I will continue with today's topic. In the last class, I have started discussing the differentiability of a complex valued function, and after that, I have discussed one new concept that we'll study only in function of complex variable, which we didn't study in function of one real variable or function of two real variable. That is the concept of analytic function. So what do you mean by the analytic function? So analytic function means if I consider the differentiability of any function, that can be a function of real variable or complex variable, we actually discuss the differentiability of the function at a given point, only at a particular point. Because if we are asked to verify whether a given function is differentiable or not in a given set, then as a whole we can't answer this question. Just we need to verify whether the function is differentiable at each and every point which belongs to that set. Then if it is differentiable in all these points which belongs to that set, then I can say that the function is differentiable in the entire set. But if we if we know the concept of analytic function, then it will be very much easier for us to provide the assurance of differentiability of a function in a given set. How we can do so? So there are three concepts of analytic function. So first we discussed about the analytic functions in a in a particular point. That means if I provide you a point z0, then the function is analytic at that point, means the function is not only differentiable at that given point, but also we can construct any neighborhood around that point where the function is differentiable at each and every point which belongs to that given neighborhood. Then compared to this, so this is more broader concept compared to differentiability, because when we discuss differentiability, we actually discuss the differentiability at a particular point. But while we are discussing the analyticity of a function at a given point, that ensures the differentiability in any neighborhood of that given point. So we are getting a broader set where the function is differentiable. After that, we have discussed much broader concept, that is called the analytic function in a domain. That means domain means collection of collection of some points in the complex plane. So the function is analytic in the domain means if I pick arbitrary point from that domain, then corresponding to that point I can construct any neighborhood where the function is differentiable. So there are lots of points in the domain. So at each and every point the function is analytic, not only at the single point. Apart from this, the most important property or important concept of analytic function is the entire function. Entire function means we are not considering a particular point or a particular set. Rather, we are providing you the entire complex domain, entire complex any complex number where the function is analytic. That means if you are given any complex number, then corresponding to that I can construct any neighborhood where the function is differentiable at each and every point. So up to this I have discussed in the last class, and I have shared also one PPT regarding the first class's PPT. Today, after this class gets over, I will be sharing the lecture note 2 and 3. So up to this, I think I have discussed. Can anyone tell whether I have discussed up to this or not?
Yes, sir. Up to this.
Okay. So do you have any kind of doubts, anyone, or is it clear? If you have any kind of doubts, you could ask me. Otherwise, I'll start the new thing. Is it clear? Whatever I have discussed in the last class.
Yes, sir.
Okay. Then, since we have told that the differentiability means differentiability at only a given point, but analyticity means in a given set. In a given set, the function fz is differentiable. So it is more broader concept, because if I know that the function is analytic, then I don't need to verify whether it is differentiable point wise. Rather, in the given entire set, we can say that the function is differentiable. So this is much broader concept compared to the differentiability of a function. So now the thing that we are going to discuss, how to check whether a given function is analytic, because since we are not checking the differential, we know how to check the differential at a particular point by first principle, but here we are going to study the characteristics of the function in terms of differentiability in the given set. So how to check whether a given function is analytic or not, whether a given complex valued function f(z) is analytic or not. How to check? So for that we will be studying one theorem. This is called as the necessary and sufficient condition. Before discussing how to check whether a given function is analytic or not, just I want to tell you one thing which is required here to study the theorem, that is called as the necessary and sufficient condition. So can you remember this? I think you have studied this in first semester when you have studied the Rolle's theorem. Have you studied this or not? Because necessary and sufficient condition is actually while we prove different theorems or provide the statement of a theorem, then these two conditions are very much essential actually. So did you study it before? Do you know it? Have you studied it earlier or not?
Yes, sir, we have studied, but I think I forgot.
Okay. Okay, so just I am briefly saying what is it, and then I'll discuss through an example which you have studied earlier. Then I'll discuss the condition for a function to be analytic. Okay, so necessary sufficient condition is roughly, let's say A is one condition and B is another condition. Another this can be a single condition or a collection of conditions. So A is one condition and B is one condition. So whenever B is holding, by assuming that if we can prove A, that is called as the sufficient condition. Similarly, by assuming A, that means whenever A is holding, if B holds, then it is called as the necessary condition. So we are considering actually, so while we are proving some theorem, assuming something, we can prove another thing. So here we are assuming, let's say B, then if I can prove A, that is called as a sufficient condition. And by assuming A, if we can prove B, that is called as a necessary condition. So just I am giving a simple example, then I think you will be able to know, able to understand these things. Okay. So you have studied Rolle's theorem in first semester. So can anyone tell me what is the Rolle's theorem? Or what are the statements of Rolle's theorem? What is the statement of Rolle's theorem? Anyone?
Hello,
Have
sir.
studied? Yeah.
Yes, sir, f of x2 minus f of x1 divided by x2 minus x1 gives the slope. I have
No, this is not
forgot.
the Rolle's theorem. This is the Lagrange mean value theorem.
Yes, sir, the condition is x1, fx1 is equal to fx2, I think, is also.
Only this is not the condition. Any other? Can you remember or you have forgot?
Sir, if f of a is equal to f of b, then f dash x is 0.
No, other conditions are there. Okay, just I am writing. There are two set of conditions. One condition is f dash equals to 0, and another set of condition is, so the given is function which is defined in the closed interval a b to the set of real number r. That means the domain is the closed interval and codomain is set of real numbers. Then there are two set of conditions. So this is a condition, that f dash is 0, and b is the collection of some conditions where it is given that if the function which is defined from ab to r should be continuous in closed ab, this should be differentiable in open ab, and number 3, f of a, that means the functional value at the given point a must be equals to functional value at the given point b. So there are two sets of condition. A is one set of condition, B is one set of condition. So we know that whenever the function is defined from AB to closed AB to R, if f is continuous in closed AB, f is differentiable in open AB, and f equals to fb, then f dash is 0. Is that so or not? Can you remember this now?
Sir, it is not also the C's lies between A and B.
Yeah, C should be in between AB. Yeah, then there exists. Okay, so, if dash is 0 means then there exists a C in closed AB. Yeah, I have not written this. Okay, that is that clear? Is that clear or not?
Yes, sir.
Okay. So this is called the sufficient condition. That means Rolle's theorem is a sufficient condition, because whenever this condition holds, then f dash is 0. That means you know that f dash is 0 if this happens, this happens, this happens. Now, if the converse is always true, that means if f dash is 0, then will these three conditions be valid? If this three is valid, then only it will be true. But if this holds, then will these three conditions be followed? What do you think?
Sir, I think it is not necessary. It
Yeah,
will
this is
follow.
not necessary,
Yes,
because
sir. Not
if f dash is 0, then f will be obviously continuous, since the f function is differentiable and it is becoming 0, and it will be obviously differentiable. But this condition, the third condition, may not be true. Okay, so that's why the converse will not be always true. That means this will not be valid. That means this condition will not be necessary. That means Rolle's theorem is sufficient but not necessary. But if both the conditions, that means if whenever this is holding, this is true, and whenever this is holding, this is true, if this happens, then we say that the theorem is necessary as well as sufficient. Otherwise, we need to identify which type of condition is satisfied here, then depending on which the theorem will be either necessary or sufficient. Is that clear? Is that clear now or not? Is it okay?
Yes, sir. Okay.
So this is called a necessary and sufficient condition. That means there are two set of conditions. One is set condition A, one is condition, another is condition B. Then whenever V is holding, if A is true, then we call as a sufficient. Whenever A is holding, if V is true, that is called as a necessary condition. Okay. Now how to incorporate this in analytic function? Okay. So here there are two type of thing. One is we are going to verify what are the conditions for a function. Function means here obviously the complex valued function fz to be analytic. So here there will be two parts. One is fz is analytic, so that is the condition A. Another will be condition B. That means there will be certain conditions. Now what are the conditions? Before that, just we need to know, while we are considering a function of one variable, then by derivative we measure actually a rate of change of dependent variable with respect to the independent variable. So up to first order there is only one derivative. So while we are considering the function of two variables, then number of dependent variable is 1 and number of independent variables are 2. So here if we want to measure the rate of change of the dependent variable with respect to independent variable, we can't measure both simultaneously. So once we need to measure the rate of change of the dependent variable z with respect to one independent variable by keeping y constant, and we need to identify the derivative or rate of change of z with respect to y by keeping x constant. So there are two partial derivatives up to first order. So while we are considering the function of complex variable, let's say w equals to fz, then w being a complex number, this will be u plus iv, and z being a complex number, there will be x plus iy. So you can write down this as u comma v equals to f of x comma y. So number of independent variable are 2 and number of dependent variable are also 2. So how many total partial derivatives will be here? Have you got my question? Is the question clear?
Sir, 4.
Yeah, there will be 4 because there are 2 dependent variables. So we can measure the rate of change of one dependent variable with respect to both the independent variable twice. Similarly, we can measure the rate of change of another independent variable with respect to both the independent variable twice. So there will be 4 partial derivatives. One is del u del x, del u del y, del v del x, del v del y. So what are the conditions here? So before that you need to know one equation that is called as the Quasi-Diamond equation or CR equation. What does it mean by this Quasi-Diamond equation? So a function fz is given equals to w, where z equals to x plus iy, and fz equals to w equals to u plus I. Then we say that the function is satisfying the Quasi-Diamond equation. The function fz is satisfying the Quasi-Diamond equation if these two conditions are satisfied. That means there will be 4 partial derivatives as I have told earlier. So if this satisfies, del u del x equals to del v del y and del u del y equals to minus del v del x, then we say that the function is satisfying the Cauchy-Riemann equation. So how to get this result? So I am not going to discuss that, but if someone wants to know how to get these results, you can contact me personally. But for the time being, you need to remember only this condition, that is called as the Cauchy-Riemann equation. So a function, complex valued function fz equals to w is said to be satisfying the Cauchy-Riemann equation if out of these 4 partial derivatives they satisfy these two equations. One is del u del x, the partial derivative of u with respect to x equals to partial derivative of v with respect to y, and partial derivative of u with respect to y is equals to minus of partial derivative of v with respect to x. So if these two conditions are valid for a given function fz, then we say that the function is satisfying the Cauchy-Riemann equation. So just I am giving one example. Let us consider the function fz equals to z square. So first we need to segregate this function in real and imaginary parts. So if I put z equals to x plus iy, so this will be x square plus I square y square plus 2x iy. So I square is minus 1. So this will be x square minus y square I. So that is our u, that is v. So what is del u del x? So here u and v both are functions of x and y. So
2x
2x. Del u del y? Del u del y?
2x
Minus 2y. Del u del y? Del u del x will be 2x. So this is u. Del u del x is 2x. Del u del y is minus 2y. So what is del v del x? V is this 2xy. What is del v del x?
and del v del x will be 2y.
Del v del x will be 2y and del v del y will be 2x. So
Yes,
here
sir.
del u del x is del v del y and del v del x is minus del u del y. So they are satisfying the Cauchy-Riemann equation. That is the Cauchy-Riemann equation. This is satisfied. So this function is said to be satisfying the Cauchy-Riemann equation. Okay. So if a function doesn't satisfy these two conditions, then we say that it is not satisfying the Quasi-Diamond equation. Now we'll come here. What are the conditions for a function to be analytic? So the two conditions are, the number one, the function fz must satisfy the Quasi-Diamond equation. That is del u del x del v del y del u del y, this one. And number two, all the four partial derivatives del u del x del u del y del v del x del v del y must be continuous. So here it must be continuous. So it must be continuous in the domain where we are going to check the differentiability or check the analyticity. So there are two conditions. Fz is analytic. Another condition is these two conditions. So if this two is valid, then from that we can prove fz is analytic. So fz, if it is an arbitrary function, then if these two conditions are satisfied, then at once we can say that the function will be analytic. So this condition is the sufficient condition. Similarly, the reverse is also true. That means whenever fz is analytic, then these two conditions will be necessarily followed. So this is also necessary. So if a arbitrary function fz is given to us, in order to check whether it is whether it is analytic or not, just we need to verify these two conditions. If any one out of these two conditions is not satisfied, then it will not be analytic. So the function, for a function to be analytic, these two conditions are sufficient. Similarly, if this is analytic, then obviously this will be followed. So here this theorem is necessary as well as sufficient. Was that clear? Have you got it?
Yes, sir.
Okay. Was it clear to all of you? If you have any kind of doubts, you could ask me. Okay. So in the PPT, this is given. So up to this, I have discussed. Oh, another thing I forgot to mention. So we have told about the analytic function. So a point, if an arbitrary point is given where the function is not analytic, then the point is called as a singular point for the given function fz. So the points where the function is not analytic is called as the singular points. Okay, then Quasi-Diamond equation I have told, and the necessary and sufficient condition to be analytic is that if the function is this given by this, so this will be analytic if it satisfies the Quasi-Diamond equation and if all the partial derivatives are continuous. Similarly, the vice versa, that means reverse will also be true. Then I am going to give one example. Okay, now we can identify the derivative. You know how we can write down the derivative as per the first principle at z0. If we want to find out the derivative, so this will be limit z tends to z0 fz minus fz0 by z minus z0. So apart from this thing, with the help of partial derivatives, we can identify the derivative. So what is the condition? So f dash z equals to del u del x plus I del v del x. If I want to identify the partial derivatives of u and v with respect to x, then f dash z can be written in that form. Now if we want to transfer this in the terms of partial derivatives with respect to y, then we can use the Cauchy-Riemann equation. Since function is differentiable, so obviously it will be satisfying the Cauchy-Riemann equation. Such for the Cauchy-Riemann equation, you know that del u del x equals to del v del y and del v del x equals to minus del u del y. So actually this is the formula for finding out the derivative of a complex valued function. Okay. Okay, so you can remember this formula. Otherwise, if you want to know how to get this result, you can talk to me. I'll be discussing this separately. Now I am going to give some examples to check a function whether function is analytic or not. Let us consider a function is given fz equals to e to the power z. So we need to check whether it is analytic or not. Okay, so this is the condition. This is the problem that we need to solve. The problem is clear. Have you understood the problem? Where we need to, what we need to show?
Yes, sir.
So for that we need to separate this function. Are you saying anything?
Hello, sir.
Yeah.
Sir, I was saying what you have written. I'm unable to understand. Fz is equal to
E to the power z.
e to the power. Okay, sir.
So first we need to separate this in real and imaginary part. So e to the power z means fz equals to e to the power z. So you know that e to the power z means e to the power x plus iy. So that is e to the power x into e to the power iy. So that means e to the power x into cos y plus, so you know by Euler's theorem we can break this, plus I sin y. So what will be u? So uxy will be here e to the power x cos y, and vxy will be the imaginary part, that is I into this. So vxy will be e to the power x sin y. Is that clear? Is it clear or not?
Yes, sir.
Now we need to find out 4 partial derivatives. So we need to check the two conditions, where the first condition is the function must satisfy the Quasi-Diamond equation, and second condition is that all the 4 partial derivatives must be continuous. Okay. So what is del u del x?
e to the power x cos y.
Yeah, del u del x will be the derivative of e to the power x, that is e to the power x, and cos y will be fixed. And derivative of u with respect to y,
E to the power x minus sin y.
yeah, e to the power x will be constant because this is a term that contains x. So the term contains that terms which contains y will be differentiated partially with respect to y, so that is minus sin. And del v del x, the same manner you can find e to the power x sin y, and del v del y will be e to the power x cos y. Now here del u del x is equals to del v del y, and del u del y is equals to minus del v del x. So these two conditions are valid, so the first condition is satisfied. So that means the function is satisfying the Cauchy-Riemann equation. Now the second one, we need to show that all these 4 partial derivatives are continuous. So here no particular point is mentioned where we need to check whether the function is analytic or not. That means here we need to show for an arbitrary point. That means here we need to show that this is entire function, because no particular point is mentioned over here. So here what is del u del x? Del u del x is this, del u del y is this. So del u del x, del u del y, del v del x, del v del y, all are combinations of exponential function and the trigonometric function in terms of cos and sine. That means sine and cos function e to the power x function. Now you know that if a function is defined at a particular point, then obviously it will be continuous, because if we can identify the functional value, then the function will be defined at each and every point. So it will be obviously, the graph will be obviously continuous. So here if you put any arbitrary value of z, that means if you take any arbitrary value of x and y, so e to the power x and cos y will be defined obviously, so their product will be defined. So that means del u del x, del u del y, del v del x, del v del y is defined for any arbitrary value of x and y. So that's why all of them are continuous. So all these are continuous for any arbitrary value of x and y. So this is satisfying the Cauchy-Riemann equation, as well as all the 4 partial derivatives are continuous. So that's why by combining these two, we can conclude that the function e to the power z is actually analytic for any arbitrary value of z. That means it is an entire function. Was that clear?
Yes, sir.
Okay. Then we need to find out its derivative. So you know that if I consider fz equals to e to the power z, the derivative will be obviously to the power z if you use the first principle. So apart from this, just we want to identify the derivative with respect to the partial derivatives. So f dash that, you know that if I want to identify with respect to the partial derivatives in x, then it will be del u del x plus I del v del x. So what is del u del x? Del u del x is e to the power x cos y, and I del v del x will be to the power x sin y. So that means e to the power x into cos y plus I sin y. So that is e to the power x e to the power iy. So this is e to the power x plus iy, so e to the power z. So in that way, by virtue of the partial derivatives also, we can find out the derivative of a given complex valued function if it is differentiable. Now if I want to identify this derivative in terms of the partial derivatives in y, then this will be del u del x is del v del y, and del v del x is minus I del u del y. So if you put these values also, you will be getting the same thing. So in that way, by virtue of the partial derivatives, we can actually identify what is the derivative of a complex valued function. Okay. Then just I want to so example. So in this problem, So the previous one is clear? I think it is clear. Okay. So now in the second problem, so that the function where z is not equals to 0, the function is defined as this, and whenever z is 0, the function is defined as 0. So this satisfying the Quasi-Diamond equation origin. At origin means at z equals to 0. But f dash z doesn't exist there. That means here the function is not analytic. Since the f dash z is not defined, that means the function is not differentiable. So since the function is not differentiable at origin, so obviously it will not be analytic at origin, but the function is satisfying the Quasi-Diamond equation. So what can be the reason? The reason can be, if I want to show that the function is analytic, then two conditions must be valid. So here the first condition is satisfied as per the given problem, because you need to show that only. That means the function is satisfying the Cauchy-Riemann equation at origin. But since all the four partial derivatives are not continuous, that's why this is not analytic. So we are going to show that. So although the function is satisfying the first condition, that means function is being analytic at origin, but it is not satisfying the second condition, that means all the four partial derivatives are not continuous. That's why f dash z doesn't exist there. So first we need to, is that clear what we need to show?
Yes, sir.
Yes, sir.
So if you segregate the real and imaginary part, you will be getting u as this and v as this. So just I want to show here separately. Uxy is x cube minus y cube by x square plus y square, and vxy is x cube plus y cube. Now here particular point z is mentioned, that means at z equals to 0 we need to check that this is satisfying the Cauchy-Riemann equation, but the function is not differentiable. Okay. So in the previous problem which I have shown for fz equals to the power z, no particular point is mentioned, but here the point is mentioned. So at z equals to 0 only we check. So here if I find del u del x, then you know that this will be x square plus y square whole square, then x square plus y square will be fixed, that will be 3x square minus x cube minus y cube by fixed 2x. So then I need to check whether this is satisfying the Cauchy-Riemann equation origin or not. So I need to check the derivative at z equals to 0. That means for x equals to 0 and y equals to 0. So if you put here x equals to 0 and y equals to 0, this will be converted in 0 by 0 form. So if I want to identify the derivative of that function, that means all four partial derivatives, by using the definition or by using the direct formula and put x equals to 0 and y equals to 0, all of them will become in the 0 by 0 form. So all the four partial derivatives here are not continuous. This is very much obvious, because in order to check their continuity, the function must be defined. But since all four partial derivatives are not defined at 0, 0, so they are not continuous. So from here at once we can say that the function will not be analytic. But we need to check that it is satisfying the Cauchy-Riemann equation at origin. But directly we can't find the derivative, partial derivative, and put the value z equals to 0, because we will not get a value. So here we need to use the definition of partial derivative. So what is the definition? So you know that del u del x at a given point AB is defined as limit h tends to 0 u a plus hb minus uab by h. That means since we are doing the derivative with respect to x partially, so y coordinate will be kept fixed at b and x coordinate will be getting changed from a to a plus h. Similarly del u del y one ab will be limit h tends to 0 u a comma b plus h minus uab, sorry, instead of h I can write down k here, bk by k. Okay. So can you remember these definitions? Can you remember this definition or not?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So here we need to use this definition. So del u del x means limit x tends to 0, y coordinate is fixed at 0, x coordinate is getting changed from 0 to x by x. So if we put here x equals to x and y equals to 0, so this will be 1. Similarly del y del u del y will be minus 1, del u del x will be 1, and del v del y will be 1. So here del u del x at 0 0 will be same as del v del y at 0 0, and del u del y at 0 0 will be same as minus del v del x as 0 0. So that's why they are satisfying the Cauchy-Riemann equation origin, but it will not be differentiable since all the four partial derivatives are not continuous at 0 0. Why they are not continuous? Because I have shown it here. That means if I find out the partial derivatives and put x equals to 0 and y equals to 0, we are not getting the direct value. We are getting 0 by 0 form. That's why all four partial derivatives doesn't exist. So there is no scope of their continuity. So here we can conclude that since the function is satisfying the Cauchy-Riemann equation, but the second condition is not valid, so this will not be differentiable. This will not be analytic. So the derivative doesn't exist here. Was that clear?
Yes,
Yes,
sir.
sir.
We need to cross verify that by using the formula of derivative. That means the first principle of derivative. What is this? So we need to check the derivative at 0. So f dash 0 will be limit z tends to 0 fz minus f0 by z. So you know that if the limiting value of this quotient at z equals to 0 exists, then only the function will be differentiable. Otherwise the function will not be differentiable. So we have put the value of fz. So f0 is given as 0. So z means x plus iy. Now we want to approach towards the point 0 0. So by path y equals to mx, we can approach to the point 0 0. So if I put here y in terms of mx, then there will be limit in terms of x only. So if you put y equals to ms and take the limiting value, so x cube will be deducted from numerator and denominator, and the limiting value will become this. So since here the limiting value is dependent on m, so if I change the path, then the limiting value will be changed. So that's why limit of the quotient doesn't exist at z equals to 0. So that's why it is not differentiable at 0. So by using the Cauchy-Riemann equation, by properties of analytic function, we have shown that it is satisfying the Cauchy-Riemann equation, but all the four partial derivatives are not continuous. That's why the function will not be analytic at origin, and we have also shown that by using the definition of derivative. Is that clear?
Yes, sir.
Uh, So in the next class, I will be discussing some more examples on analytic function. So up to this, I have discussed. So I have shared only one class note. So in after this class gets over, I will be sharing the remaining two class notes in the Google Classroom, so I can go through. So just let me check your attendance manually. Then I will be giving the exam codes. Rule number one. Rule number one. 2, 3,
Present, sir. All three.
4,
Present, sir.
5, 5, 6, 7,
Present, sir.
6 or 7. Rule number 6.
Sir, present, sir. Roll number 6.
7, 8,
Yes, sir.
9,
Yes, sir.
10,
Present, sir.
11,
Present, sir.
12,
Present, sir.
13,
Present, sir.
14,
Yes, sir.
15,
Yes, sir.
16, 17,
Present, sir.
18,
Present, sir.
19,
Present, sir.
20,
Present, sir.
Okay, so this is the link and this is the exam code. So just click the link and provide your full enrollment number and exam code and complete the class test. So someone from you just check and let me know whether you can access it right now or not.
Sir, roll number 15 is present.
Have you responded?
Yes, sir, I have responded,
So I
but
have
I
given,
think
so
it
why are
is
you
not
asking
heard.
again? So if you have responded, so it will be given.
Sir, I think it is not heard properly. I think that.
So how you can assume that? If you have responded, so like others, I have given you attendance also.
Okay, sir.
So someone just check and clarify whether you can access it
Yes, sir,
right.
it's working.
Okay, thank you, Sam. So finish the class test quickly. So thank you all for attending the class. So I'm leaving. Thank you.